Assalamu alaikum. I'm representing irreversible unimolecular type first order reaction, in which we will discuss kinetics of unimolecular reaction. The first order reaction will also drive its formula, and will do some related numerical problems as well. So moving towards our topic. So we will call first order reaction when the reaction depends upon the first power concentration of a single reactant. Suppose we have a reaction A to product, we have a single reactant A. This reaction can be defined as some reactant A gives product, then our rate of reaction is minus R is equals to minus dC over dt, where minus sign shows that we are discussing about reactant, so definitely its concentration is decreasing, which will also be equal to kCa. Here for 1 mole n is equals to 1, and we know that this rate represents the kCa to the power n. Here for first order reaction, this n is equals to 1, which is representing the order of reaction. So this is our differential equation. We will solve it by variable separable differentiation. So shifting Ca in denominator and negative sign to the right, we will integrate it with a definite intervals. Since we know our initial concentration is Ca naught at time t is equal to 0, and at a particular time t, let's suppose t, our concentration will be Ca. By integrating and putting limit this equation, we will get ln Ca minus ln Ca naught equals to minus kT, and in the next step we will get our final equation, which we will name it as equation number 1, which is ln Ca over Ca naught equals to minus kT. Now if we consider ln Ca over Ca naught as m, and we compare this equation with y is equals to mx and plot a graph. So since graphs are very important in CRE, we can show the reaction kinetics. And we all know that if we have a slope like this whose line lies in second and fourth quadrant, this slope is definitely negative. And if we have a slope like this whose line lies in first and third quadrant, this slope is positive. So if we have t on x-axis and ln Ca over Ca naught on y-axis, we have formed such a graph from equation number 1 whose slope is negative, and this line is actually passing through the origin from second to fourth quadrant. If we will reconsider this equation and by shifting minus sign to left side, this become ln Ca naught minus ln Ca, and by solving this equation, it is in logarithmic form, this will become ln Ca over Ca naught equals to kT, and the graph, which will be represented as given in the below, as it is showing us a positive slope. As we have derived previous equations in terms of concentration, similarly in terms of conversion, the rate equation becomes dxa over dt equals to k into 1 minus xa, which on rearranging and integrating in definite intervals, the equation we get in the end is minus ln into 1 minus xa equals to kt. In this slide, if we further solve equation number 1 by putting exponential on both sides, ln and e will cancel out each other on left side, and at the end the equation which we will get will be Ca equals to Ca naught, E to the power minus kt, which we will name as equation number 3. And what we will see that the equation we get in terms of concentration is an exponential form, where the previous equations were in logarithmic form. And further we will put a graph to see what actually we are estimating from this equation. And so we are considering the time t in x-axis and CA and on y-axis. So we are watching that at initial time, means when t is equal to 0, at its initial time when the reaction has not started, what we are saying that the concentration of reactant is maximum, which is Cn naught. Means at time t equal to 0, the concentration of reactant will be maximum, and when the reaction will proceed forward gradually, the the concentration will be decreasing. Concentration will be decreasing of reactant with uh, respect to time, and at that time equal to t. If we see how much conversion is taking place, we reconsider the equation. This equation is, we are talking about constant volume system, so we will replace Ca with Cn naught into 1 minus Xa, which we have derived previously. So by solving this, Ca naught and Ca naught will be cancelled out, and we are making subject to Xa, and by shifting all the terms to the right hand side, the equation we get is Xa is equals to 1 minus e into e to the power minus kt, which has become equation number 5. This equation is in conversion form and is telling that the value of x will be lies between 0 and 1. Means the minimum value of x will be 0 or maximum value of x will be 1. The value of x the value of x will be 0 when the reaction is not been started, means at its initial point, and the value of x can be 1 when all the concentration of a reactant, of any reactant, is converted into product. And here the graph is showing the same, that it the value of x will be maximum at 1 and will be minimum at 0 at any time t. Now we will discuss some numerical related problems of which we have learned. Let's consider a problem regarding first order reaction. The initial concentration of a reactant in a first order reaction is 1.25 molar. The rate of constant K is 0.02 per minute. Part A says what will be the concentration after 1.5 hours. B in D, how long will it take the concentration to be reduced to 0.50 molar. So moving towards our solution of part A, here we have equation number 3, Ca over Cn naught equals to e to the power minus kt. Now on rearranging this equation for Ca at given time t in question, since C is given in hours, but we have to convert it into minutes as given in the question already. 1.5 is equals to 60 which is equal to 90 minutes. So we put in replace of t here is 90. The value of Ca naught is given in data is 1.25 and value of K is 0.02. On solving this whole term, we get answer is Ca is equal to 0.2066 molar. And moving now for part B, we have to find time at given concentration. So we have equation number 1 for solving this question. ln Ca naught over Ca equals to minus Kt. We will put all the given values in equation, and by solving this, simply we get time equals to 45.8 minutes, and that is our answer. Thank you.